Bam! Mr. Tarrou. In this algebra lesson, we are going to be creating systems of linear equations. That means that we're going to be looking at two equations and two unknowns. We're going to do 4 examples, the last one of which we are going to solve. The first 3 that we come up with, we're just coming up with the equations from these word problems. Very often the biggest stumbling point of algebra students as they start learning these types of questions. In the subsequent videos, we're going to be talking about solving linear systems with graphing, solving linear systems with substitution method, and then finally finishing up with the elimination or the linear combination method. And we're going to bring back some of these systems of equations as we revisit those techniques of how to solve a linear system of equations. Now, as we do this, we're going to be reading the problem slowly and trying to understand the situation. Are we talking about some kind of geometric situation? Is it something dealing with money, maybe that can relate to our everyday lives? We're always buying stuff and going to the registers. Maybe we can set those up through our experiences of our day-to-day life. We're going to be identifying the question that is being asked for and use that question to define the variables, because the question, of course, is solve for something that's a value which you do not know. And that's what a variable is, a letter that represents an unknown or variable value. Write equations to model the situation. That's where we're going to stop. And then in subsequent videos, and you'll find links to those videos in the description of this lesson once they are posted, you're also going to find timestamps to skip ahead to each of the 4 examples that are in this video. We're going to solve those systems of linear equations, again, graphically, with substitution and elimination techniques or linear combination techniques as we go through our next few videos. We're going to be checking our answer in both of the equations. When you're talking about linear systems of equations, you're trying to find out where 2 lines cross, and thus if they do cross, you'll be looking for that unique x, y coordinate. And that's why you want to check your answer in both of those equations. We're looking for where 2 lines cross, and then we're going to summarize your answers in the context of the problem. If you have, like we have here, a word problem, then when you just find some variables, it's not just a regular sort of x and y, where it's just a generic independent and dependent variable. Those are going to be applied to something in that real world setting. Now, I know we haven't done any examples yet, but the best way of learning how to set up word problems is consistent and constant practice. So I'm going to give you just a second. Why don't you take the notes down, read the example, and try and come up with the equations on your own. We're going to read slowly, understand the situation, look for the question in the problem. That's going to help you define what the variables are going to be, and make sure you write those definitions out. If it's a situation that we're comfortable with, or even not, hopefully we can figure out what those equations are going to be. And now, again, we're talking about a system. So we're going to have 2 unknowns, and we're going to have 2 equations. So here we've got, you have $300 to spend on shirts and pants. If the shirts cost $23 and pants cost $35 and you leave with 11 items, how much did each of those items cost you? Or excuse me, not cost, we were given that $23 and $35, but how many of each of those items did you buy? Well, did you read the problem slowly? Did you try and identify what the question is asking for and define the variables? Well, we're dealing with money. We're going to the register. We're going with a collection of items which are going to then cost us some money. Do we have any information in this word problem that's dealing with money and dealing with a total number of items? Because, well, we may just buy some pants, and we may just buy shirts only, but I'm going to guess it's probably a combination of the 2. So we have information here about 11 items, and we have information here about $301. I think that would be a total amount. And then we also have some information here about, let's pick white or orange, and we have something about shirts are costing us $23, and we have, let's see, hopefully you can see the green on camera, we have pants that are costing $35. Well, that's a lot of numbers in this problem. What ultimately are we going towards, the final goal of our problem? Identify what the question is asking for. Well, you're asking for how many of each item did you buy? How many pants? How many shirts did you purchase? Well, if those are unknown values and they can vary, clearly, we have some different amounts of shirts and pants that we can buy to fall underneath that umbrella of 11 shirts, but at the same time, we have to satisfy the fact that we're spending $301. So the question really, how many of each item did you buy, allows us or tells us how to set up our variables. So in orange, we're going to say that, you can use S, you can use X. A lot of times I don't use the letter S because they'll end up looking like 5, so I'll kind of make this extra squirrely, and we're going to say that S is equal to, and if it said how much did each item cost, then S might be how much your shirts cost, but we know what that is. We're trying to figure out how many did we buy. So S is the number of shirts. And if we're buying shirts and pants, I think it might make sense to just let pants be the letter P. All right, so we have our variables defined by the question, how many of each? What numbers are in here that kind of sound like you would have to do some math to figure them out? I mean, we have $23 for a shirt, but a shirt is $23. I don't need to set up any kind of math to figure that out. We're buying 11 items. Okay, so maybe we want to set up an equation for the number of items. So in terms of buying a total number of items, then we can say, well, we have an unknown number of shirts plus an unknown, see, it almost looks like a 5. We have an unknown number of pair of pants, and together that comes up to 11. Okay. Now, that's fine. And looking at this equation only, we might say, well, maybe I bought just simply 11 shirts. Now, I'm getting a little bit off track because I said we were just going to set up these equations, but let's just talk about this for a second. If we said that we bought 11 shirts and 0 pants, that satisfies the condition that we've bought 11 items, 11 shirts. But if you take, a shirt is $23 and then $23 and then $23, and every shirt that you go up to the register with, they're going to add $23. Well, that repeated addition is multiplication. So what would be your cost for just buying 11 shirts? Well, that'd be 11 times a shirt is $23. Well, I don't have a calculator, and I really didn't mean to do this, shoot off on this tangent for this example. So if I'm going to do 11 times 23, what I'm going to do is break the 11 up into two numbers and do 10, because that's the tens place, times 23 is equal to $230, because that's $23 for shirts. And that's so 10 shirts are costing you $230 plus an additional 1. Well, those first 10 shirts plus the additional 1 shirt to make it a total of 11 is $253. So that particular combination of 11 shirts and 0 pants, while meeting the requirement of buying 11 items, does not meet the requirement that we've spent $301. And indeed, I can say 11 and 0, 10 and 1, 9 and 2, and so on and so on, and really actually solve this particular question with a table of values, keep going until I get a combination that matches that 301. And in this particular situation, I know the answers are whole numbers, so that sort of table idea to get your way to the answer will actually work. But if the intersection point of these lines contains decimals, or even worse, irrational numbers, you're not going to find that very accurately with just doing a table of values. So we set up two equations, one for the number of items and one for, well, we've got a total amount of money. So let's talk about money. In terms of money, well, we kind of already alluded to the fact that repeated addition, every shirt adding an additional $23, that repeated addition is multiplication. So S being, let's see, I don't remember what S was. Oh yeah, that's right, I wrote it down. S is the number of shirts. And if each shirt is $23, then the amount of money I'm spending on shirts is $23 times the number of shirts. Now, having an S dollar sign and an S variable is kind of confusing, I think, looking. So I'm just going to write 23S, but it is $23 for each individual shirt. Plus, well, pants are $35, and you're going to spend $35 and $35 and $35 for every pair of pants. That repeated addition of 35 is multiplication. Now, the amount of money for shirts plus the amount of money for pants is going to come out to be a total of $301. And that is your system of equations. Now, second example coming up right now. Voila! A rectangle, rectangle's, there we go, length is 2 inches less than 3 times its width. If the perimeter is 28 inches, what are the dimensions of the rectangle? So again, pause the video, give this a shot, try and come up with these examples on your own. I'll be right back to talk about the solution. So I hope you got it, and if not, let's figure it out. A rectangle's length is 2 inches less than 3 times its width. Okay, that seems like there's a sentence there with a lot of math in it. Hopefully we can pull an equation out of there. We're clearly talking about length, and it is, whenever you have the word is in an equation, that, or excuse me, in a word problem, that almost always identifies an equal sign, and it's 2 inches less than 3 times its width. Oh yeah, I better not start talking about the solution to this problem unless I do a couple of things. Number one, I need to get to the end of the question, read it, and figure out what is it I don't know, what is it I'm trying to find. That is going to be the unknown variable, thus that's what the variable is, a letter that represents an unknown value. So the dimensions of a rectangle, well, we are going to be talking about a rectangle, so it'd be probably nice if we had a picture. And there's a rectangle, the opposing sides are congruent, and all the angles are right angles. It's this type of parallelogram. And we're looking for the dimensions. Well, when you describe, a picture frame, is it 8 by 10, 11 by 14? Those two numbers represent the length and the width of the rectangle. And so when we ask about the dimensions, we're asking about, well, how long is it? So L is going to be equal to, where's my unit of measure? Inches. So L is number, well, I'm going to write the pound sign, I'll write the word the next time, number of inches in length, and then W, well, that'll be the width. Awesome. Well, now the variable's defined. Clearly we have a sentence relating the length, L, the length in inches, to 3 times its width. So a length is, first thing in the sentence is length, the next word is, that's going to be our equal sign, 2 inches less than 3 times its width. Now I have videos about creating equations from word problems. It just wasn't a system of equations, and we've talked about before how this less than, more than phrase, well, more means more to add to, and less is to take away. But with this 2-word phrase, let's not forget that we're going to have to change, well, and I'm going to break all my yellow chalk in this video, we're going to change the order of the problem. If I have $10, let's say, and you have 2 less than I do you have 8 or do you have -8? I have 10, and we're going to start with you have 2 less than what I have. I started with 2 less than. So if you do 2 minus 10, first thing in the sentence was 2 less than 10, you come out to be -8. Saying someone, well, you could owe money, which is effectively a negative number, but if we're going to kind of say, well, if I have $10 and you have 2 less than what I have, keeping the subtraction in the same order doesn't make any sense. If I had 10, you would have $8. That's 10 minus 2. You change the order around. So less than will be minus, but and with the 2 being first, it's actually going to become second. Again, that order is changing. 2 is before less than, but in the algebraic expression, it's after. And it's 3 times its width. So we don't know specifically what the length of the rectangle is, and it might be nice if I put maybe a L in here for length and a W here for width. I don't really know either measurements, but I really know nothing about the width. But I do know that the length is 2 less than 3 times its width. So when I come back over here to the diagram, I can say, well, length is equal to 3W minus 2. Now, I'm kind of setting up an expression here that will be reviewed when we talk about solving these systems with substitution. But for now, I want to, get the setup out of the way. I teach a lot of levels of math. I kind of want to jump right to the answer. But in terms of the setup, we have an equation from the first sentence. Now talking about if the perimeter is. Well, what is the perimeter of a polygon? It's just the sum of the outside segments all added together. Now, I have this 3W minus 2 written here, and you might want to just say, well, it's W plus 3W minus 2 plus W plus 3W minus 2, and you would be correct, and you would get to the, you'd get an equation with only one variable in it, and you'd be able to immediately go to solving one of the two variables. But we're focusing on getting those two unique equations set up before the substitution has happened. So perimeter, with perimeter, let's do this in a different color. With the perimeter being, well, let's see, perimeter is, for a rectangle, 2 times the length plus 2 times the width. Perimeter of any polygon is just add all the sides up, but with a rectangle, the opposing sides are equal, so you can say 2L plus 2W. And in this particular problem, the perimeter is equal to 28. Now I'm kind of actually doing a substitution right now. I'm going to take the P out and in its place put in what we're saying that it's equal to, which is 28. And indeed, as you go through your studies of math, algebra, geometry, algebra 2, all the way up to calculus and beyond, whenever you're given a number that has a formula attached to it, you're going to use that formula in the problem. That's a good hint on how to set up your equations. And these are going to be the two equations. One is, another chalk down, something about the length related to the width, and the other one is about the perimeter. And I've already kind of, with this diagram, alluded to, we will be revisiting this question when we talk about solving systems of linear equations with substitution. Like we took the P out and plugged in 28, we're going to take this expression of 3W minus 2, which is equal to L, and plug it into this equation for L. And we would have an equation with only one variable in it. We'll find W first, and then from that find L. But I'm getting ahead of myself. Let's get to the third example. Ta-da! This is another setting that we are really familiar with. You don't have to understand a little bit of geometry to be able to solve the problem. It's spending money. It's going to the store, or in this case, purchasing and renting some items online. John purchased 7 songs and rented 3 movies online and spent a total of $33.63. Tania purchased 5 songs and rented 4 movies and spent a total of $37.95. How much did each song and movie cost? So where before we were given how much the shirt and the pants cost, and we were asking to solve how many of each did we buy. Here we're told how many we bought or rented, and we're looking for the price. And money, as we can see, has some crazy decimals. So you definitely would not want to try and find the price of the movies and the songs with graphing or a table of values. You're going to want to get those decimals through substitution or linear combination. So how much did each song and movie cost? Well, let's again, as much as I don't really like to use variables or letter S as a variable, because they look like 5s for me, S equals the amount of money each song cost, and let's just say M for movie. Great. We've got 7 songs and 3 movies for John. So let's write all of John's work values related to John in orange. So 7 songs, 3 movies, and he spent a total of $33.63. So it's almost like John is sort of, he's not really a variable, but we can help use the names to organize our work. So we're going to write an equation related to what's going on with John. What is going on with John? Well, he rented 7 songs, and every song he's going to rent, or excuse me, buy, is costing him money. So whatever that unknown value is, it's something plus something plus something plus something plus something plus something plus something 7 times, and adding something together 7 times, repeated addition, is multiplication. So that is going to be 7 times S, how much money each one of those songs cost. And to that, there's money, because again, money is in the definition, that he spent on songs, came along, and you spent some more on movies, and that's going to be 3 times the number of movies. And he spent a total of $33.63. Now, what about Tania? Well, Miss Tania, she purchased 5 songs, she rented 4 movies, and she spent $37.95. So, how do you make up Tania's bill? Well, every song has a value cost with it over and over and over again 5 times. It's going to be 5 times how much each of those songs cost, plus the 4 movies that she rented, giving her a total bill of $37.95. Now, give you a preview, not really a preview, but I'll say it later for my students and for you all, so you won't be hearing it for the first time. When you look at these linear systems and you try to decide whether you want to do linear combination or elimination, or substitution, the linear combination and elimination are the same thing. Just depends on what textbook you're using. None of these coefficients, that's the number in front of a variable, none of these coefficients are equal to 1. So while you could solve this system of equations with substitution method, I would prefer, and it will be easier for you as well, more than likely, to solve this system with elimination. So this is going to come up again when we talk about solving linear systems with the elimination method. We got one more example. That one we are going to solve, and it's going to be dealing with distance equals rate times time, or D equals RT formulas. At 1:30, Tom leaves in a boat from a dock and heads south, traveling at a rate of 22 miles per hour. 20 minutes later, Mary leaves the same dock on her boat and heads for Tom. If she travels at a rate of 30 miles per hour, when will she catch up with Tom? Now, if you have done distance equals rate times time problems, and you feel like you might be able to figure this out, why don't you just pause it and try it yourself? All right. But for the rest of us, and to check your answer maybe, if you did pause the video, we're going to remember that anything in motion related to, we're going to be, when will she catch up? Well, she's going to catch up when she travels the same distance. We have rates of speed, and of course, when is a time value, so it's going to be distance equals rate times time. And to give you a visual of what's going on, it's like here's a dock here, and here goes Tom. He gets a head start, and then a little bit later, here comes, what did I use? Mary. And here comes Mary, and Tom's going at 22 miles per hour. Well, Mary is going to be going faster, and at some point, she's going to catch up, and they're going to go the same distance. So let's use what little piece of brand new yellow chalk I have left because I keep breaking it and talk about Tom. Well, Tom leaves a boat from a dock and heads south, traveling at a rate of 22 miles per hour. So that's going to be a rate for Tom. And as an older, 20-year math veteran teacher, I'm used to just saying, with lines, there's slope, rise over run. Well, then you start teaching like I teach AP statistics, and slope is the average change in y per 1 unit of change in x. And I'm starting to see now that I'm teaching Algebra 1 again, that saying slope all the time is kind of like a bad word in Algebra 1. Apparently, they call everything a rate of change. Well, rate of change, or again, the idea of rise over run, is some kind of change in y, and when you have time in your problem, that's generally going to be the x-axis. So we have a change in y per, and the word per in a word problem is always some kind of division. So it's miles divided by basically the number of hours. And indeed, if you take this formula and solve it for r, which is a rate, you're going to divide both sides by t and get a particular distance over time. Whew, okay, so Tom is going to travel some kind of distance. Tom's going to be in yellow, and that's going to be equal to his rate, which is 22 miles per hour, and it's going to be multiplied by some type of time. Now, I'm starting to realize that I'm doing the same thing I did in the previous video, which is I'm not defining my variables. So I've said I've done it in yellow, but what we're going to do is I'm going to go ahead and say something like, well, in my notes I did d sub t is the distance, I just can't print, Tom traveled. So let's put a little subscript of t in there. I'm going to do it in color coding with yellow anyway, and then let's do blue, or I think blue will show up pretty good against the yellow. We're going to do blue for Mary. And if she travels at a rate of 30 miles per hour, when will she catch up with Tom? That kind of means that we're going to need a time and a distance for Mary as well. So maybe we would do something like, just again, consistent with everything in color coding, T sub n is going to be time, again for Mary, and T sub m is going to be, T sub t is going to be a time for Tom. So yellow, Tom, blue, Mary. Now, we got distance equals rate times time for Tom. Now, we come along here and it says for Mary, this would be a really advanced problem for Algebra 1. This might be end of Algebra 1, maybe even the beginning of Algebra 2. But I just thought I'd throw that out there in case you happen to see it in your books. 20 minutes later, Mary leaves the same dock, and on her boat, and she heads for Tom. So we're going to set up an equation for Mary. Now, we're going to do Mary in blue. We're going to have to deal with that 20 minutes later thing. She's going 30 miles per hour, and I realize I'm going to need to pause here and change my definition of my variables, because it's kind of like I'm doing yellow for Tom, blue for Mary. Mary is going to cover some kind of distance. Mary is going to be going 30 miles per hour, and she's going to be traveling some amount of time. Now it says that she traveled 20 minutes later, she left 20 minutes later. So you might go, well, let's see. Whatever amount of time Tom drove the boat, Mary went 20 minutes later, but that's going to get you the wrong answer, because it's not 22 miles per minute, it's 22 miles per hour. So we need to change that 20 minutes. We can't have questions in terms of hours and minutes in the same problem, so we're going to have to fix that. And we're going to have to fix the fact that if Mary catches up with Tom, they've actually gone the same distance. So having two different variables for distance in this particular problem doesn't really make any sense, because she catches up, thus they've traveled the same distance. These problems aren't necessary. These problems aren't easy, and even experienced people maybe not be the smartest person on the planet, but we'll sometimes need to revisit and redefine what's actually going on. So, to follow my own advice, it's when will she catch up with Tom? So, Tom, let's do T, that's going to be T hours. And for Mary, I'm kind of doing the substitution as I go through this problem. Instead of writing something like, you know, D equals 22T and then something like D equals 30M is sort of weird because like time for Mary. So Mary traveled, well, she left later, so it's going to be whatever amount of time Tom travels minus some value. And what is 20 minutes in terms of hours? Well, 1 hour is equal to 60 minutes. So 20 minutes is going to be some part of the 60 minutes, which makes up the entire hour. Well, those both end in 0, and 2 6 reduces down to 1/3. So that means that we're looking at 20 minutes later is 1/3 of an hour later. So Mary traveled whatever amount of time Tom traveled minus 1/3 of that hour. Now here we go. So we're going to say that we've got Tom traveled a distance 22 miles an hour for a set period of time. Mary, well, I'm going to keep that in blue. She covered the same distance because she caught up to him, going 30 miles per hour for that amount of time minus 1/3 of an hour. I hope that's making sense. Well, we're going to, let's solve for that amount of time. This equation's equal to D. This equation's equal to D, and you're getting a taste of what it is to solve a linear system with something called substitution. We're going to take this expression right here, it's equal to D. So since this expression is equal to D, I'm going to take that expression and plug it into the other equation. Well, if it's equal to D, I'm going to find D in this other equation. There it is right there. And plug it in, substitute it in. D is equal to 22T. So this D is going to come out, and in its place, 22T. Now we have one equation with two variables, distance Tom traveled and the time that he traveled, and the distance that Mary traveled and the time that she traveled. With that substitution, we now have one equation with one unknown. So we're going to distribute the 30. That's going to be 30 over 1 times 1/3. And the 30 over 3 reduces to be 10, or 3 divided by 3 is 1, and 30 divided by 3 is equal to 10. So we're going to subtract both sides by 30, T, and get negative 8T is equal to negative 10. We're going to divide both sides by negative 8 and get T is equal to, now a negative divided by negative is positive, so those are going to cancel out. We can reduce this, these are both even, so we can divide the numerator and denominator by 2, and we get 10 divided by 2 is 5, 8 divided by 2 is 4. That's a mixed fraction, or you can divide that, how many, 4 going into 5, or 5 divided by 4, well that's 1. There's your 4, subtract, and a remainder of 1. So that's going to be T is equal to 1 and 1/4. Well, what's 1/4 of an hour? When you're doing word problems, you need to remember that this isn't just naked math. This is all applied to some kind of real life application. So T is not just 1 and 1/4, it's 1 and 1/4 hours. Well, that going back to the idea of, maybe dealing with something in terms of minutes, that is 1 hour and 15 minutes. Now, I'm putting a box around that, but that doesn't necessarily mean that's the answer. This is where I misspoke in the previous video. We need to make sure we understand that, wow, I got some variables defined. I messed it up a little bit there in the beginning, but we got some equations, I've done some math, and I got a number. Wow. What does that mean? And are you even answering the question? Well, it says, if she travels, Mary, if she travels at a rate of 30 miles per hour, when will she catch up with Tom? Doesn't ask, how long is she traveling? Just simply, when will she catch up? Well, let's see here. Just T was Tom's time. And that's sort of how the whole problem started. Tom was on the water T hours, in his boat traveling for T hours. And T actually does come out to be 1 hour and 15 minutes. So she's going to catch up with him in that amount of time. So she's going to catch up with Tom at, 1 hour and 15 minutes after 1:30. So 1:30 in an hour is 2:30, and 2:30 in an additional 15 minutes is 2 o'clock or 2:45 p.m. And you're kind of looking at a fairly complicated setup on this problem, a complicated design of this problem, and a substitution technique. You've got one equation, D equals 22t, and D equals 30 plus t minus 1/3. Both of these equations having the same variable of D because she catches Tom. He starts ahead, she eventually leaves, she catches up, she goes faster, and eventually they cover the same distance. And we could figure out how long Tom and Mary traveled, but that's not part of the question. We could say how long Mary traveled. That's also not part of the question either. But if Tom, T, this is where I got messed up on the other video, T is for Tom, and if he was in the water for 1 hour and 15 minutes and Mary left 20 minutes after he did, well then she was on the water for 55 minutes. That is the end of my last example. I'm Mr. Tarrou. Bam! Go do your homework.